Okay, so continuing on with our electromagnetic radiation, we or electromagnetic waves, same difference there. Sorry, I realized I've been using those interchangeably. Waves, radiation, either one works. Our next section is looking at the speed of light, and it turns out this was experimentally observed in 1926 with an American scientist named Michelson. He was down in Los Angeles, so Southern California, and he set up on Mount Wilson, which is where this red dot is, and Mount San Antonio, which is over here. On one of them, he put a rotating octagonal mirror. The other, he put a fixed mirror. And the distance between these two peaks is 35 kilometers. So pretty good distance. And so then he sent light from a source into the mirror. And when the rotating mirror was at just the right position, right, it was able to reflect to the mirror and then reflect back. And so based on timing that rotation and the flashes of light that he was able to make this measurement of the speed of light in a vacuum. That it was 2.99792,458 times 10 to the 8 meters per second, which is pretty close to the value we've been using. So that was the experimental value. And the fact that this is not just infinitely fast has some real implications, as I alluded to in class last week. So this conceptual example takes a look back at this in time. The supernova is a violent explosion that occurs at the death of certain stars. The figure shows a photograph of the sky before and after, a few hours after a supernova. Why do astronomers say that viewing an event like this is like looking back in time? It's pretty wild, right? Before, we can see the star, and then after, we see a supernova. And this is a neighbor galaxy that's 1.66 times 10 to the 21 meters away. So now I want you to reflect on this yourself, on why this is looking back in time, and see if you can come up with some supporting evidence for that. So go ahead and pause now. Okay, hopefully you paused. Well, one thing we could think about here is the relationship between distance and time. And we could show that time, whoops, I'll stop moving the mouse down there. Time is equal to distance divided by velocity, right? This comes from the definition of velocity being distance over time, and then we swapped the time and the velocity. So if we plug in for our distance, the distance to that neighboring galaxy, the 1.66 times 10 to the 21 number, and then we divide by the velocity, which is not infinitely big, but is still very large at 3 times 10 to the 8 meters per second, we come out with a huge number of seconds. If you do the calculation, it's 5.53 times 10 to the 12 seconds. But if you convert that to years, which are easier to understand, to 175,000 years. So even though these photographs were taken in 1987, this occurred almost 200,000 years before that. Super far look back in time. So that's pretty amazing, and it's using this relationship between distance, time, and velocity, which we can go back and forth between those variables. And there's a homework problem that uses a similar relationship. Right, now Maxwell, another scientist, made a theoretical prediction of the speed of light by combining equations, and he came up with this equation that the speed of light c is equal to 1 divided by the square root of epsilon naught mu naught, where epsilon naught is our permittivity of free space and mu naught's our permeability of free space, right? We saw the epsilon naught with our electric fields and the mu naught with our magnetic fields. And with this combination of them, he gets that the speed of light is exactly 3 times 10 to the 8 meters per second, which is remarkable. And so this confirms the experimental, or the experimental confirms this. They work right in alignment with each other, which is great. And it tells us that light behaves as a wave of oscillating electric and magnetic fields. It turns out within light, the electric and magnetic fields are related by the speed of light c. So if you know the magnetic field strength, you can multiply by c and get the electric field. Or if you know the electric field, you can divide by c and that would give you the magnetic field, which is pretty remarkable. That applies anytime you have the electromagnetic waves occurring. And that's a pretty good point to wrap up. So we'll pause there because that covers the speed of light. See you next time.